Hello, I'm Michael Gamlen and I'm here today to welcome you to the Gamlen Dashboard, a tableting revolution from Gamlen Instruments. Making just one tablet can tell you all you need to know about manufacturability for both new and existing tablet products. In many cases, one tablet can tell you whether your new product is good enough or whether your existing product is the same quality as a previous batch. The Gamlen Dashboard has been developed to work with the Gamlen D-Series Powder Compaction Analyzer, combined with the Gamlen Tablet Tensile Analyzer, a unique system for characterizing powders. The Gamlen Dashboard is used to visualize your data in real time. It brings together all of the tablet's data into a single manufacturability analysis and places the product on 8 critical quality attribute scales, which are the key to determining both product quality and the risk of product failure. The quality of a tablet is assessed using 2 key measures: compressibility and lubricity. Material compressibility is needed to ensure that the tablet is robust and can withstand handling and delivery to the patient. Lubricity is needed to ensure that the tablet does not suffer from lubrication problems during manufacturing, such as picking, sticking, and lamination. A tablet blend also requires adequate flow. The Gamlen D-Series instrument measures punch position, punch force, tablet detachment force, and tablet ejection force. These are all of the parameters needed to fully assess tablet quality for formulation development or quality control purposes. The working load of the D-Series instrument is 500 kilograms and the maximum operating speed is 3 millimeters per second. It can be used to make tablets from 2 to 15 millimeters diameter and uses a proprietary punch and die system with flat-faced punches. Using the Gamlen D-Series, we normally make small tablets at the same pressures as are used during production manufacturing. For our data to be useful, we needed to check whether making small tablets gives the same tablet properties as larger tablets. One very important tablet property is tablet tensile fracture stress. This is measured using a method first published by Professor Mike Newton. Professor Newton used it to distinguish between different size fractions of the same sample of lactose. This is a very difficult test, showing that the method is very discriminating. In the graph on the screen, you can see data from a study in which we looked at 3 mm and 6 mm tablets. I've plotted the tensile fracture stress of the Avocel pH-102 tablets made at a range of compaction pressures. You can see that the data from the 3 and the 6 mm tablets lie on the same curve. Using this study, combined with data on tablets of other shapes, has shown that the tensile fracture stress of a tablet is independent of tablet size for tablets of 3 mm diameter and upwards. So we can use data generated on small tablets on the Gamlen instruments to accurately predict the properties of large tablets. We also wanted to make some comparisons between the properties of tablets made on our system and the properties of tablets made on the production scale. We were very fortunate to have the assistance of Dr. Kendall Pitt of Glaxo Manufacturing Services, who generated and published some test data with us. In this example, we compared the tablet tensile fracture stress of 100 mg 6 mm diameter tablets made on the Gamlen instrument with an 800 mg capsule-shaped tablet made under production conditions on a Fette 2080 press. Again, the data lie on the same curve, despite the differences in speed, weight, and tablet shape. In this plot of compactability, which shows tablet tensile strength as a function of tablet density or solid fraction, the data from the production fete and the Gamlen instrument again lie on the same curve. We have made a number of other comparisons with different tablet presses and shown that the data generated on the Gamlen instruments is generally predictive of production behaviour. The instrumentation system on the D series continuously logs the punch position and the punch force during compaction to generate a complete record of the compaction process. In normal operation, we manufacture a series of tablets at different compaction forces to determine the effective compaction force on both the compaction process and the tablet properties. We produce a complete compaction, ejection and detachment profile for each tablet. From this, we extract the peak compaction, detachment and ejection forces. We also calculate the ratio of the ejection to the detachment force and the compressibility as defined in the USP compaction monograph. This is the density of the tablet as a function of the compaction pressure. Detachment stress, sometimes called takeoff force, is the force needed to detach a tablet from the punch tip during manufacturing. If detachment stress is too high, defects such as picking and sticking are seen. The relationship between ejection stress and detachment stress is also important. Ejection stress is the stress generated during the ejection event. It is a measure of how well lubricated the tablet is. Lubricants are added to the formulation to reduce ejection stress. Poor lubrication results in picking and sticking problems during production. This is one of the most common tablet defects, which results in slow running of the tablet press and reduced output. High ejection stress, more than 5 megapascals, has been found to be strongly correlated with manufacturing problems. E to D ratio is the ratio of peak ejection to peak detachment stress. Most materials have an E to D ratio of close to 1, in the range 0.9 to 1.1. However, some materials have values markedly different from 1, as low as 0.5 or as high as 2. A low ratio, when the peak detachment stress is a lot higher than the peak ejection stress, is associated with picking and sticking. Compressibility is the relationship between tablet compaction pressure and tablet density or solid fraction. This has been analysed to try to understand the compaction properties of materials using methods such as the Heckel analysis and the Kawakita analysis. This is the Gamlen Dashboard. It is a display which gives a real-time view of the compaction properties of the material while it is being tested on the Gamlen D series. Our recommended way of working with a new material is to test 5 tablets at each of 5 compaction pressures to give a comprehensive picture of the material properties. As each tablet is compacted, the values from the tablet pop up on the screen. Here we see some typical data for a sample of lactose at the compaction stage of the test. You can see that there are 4 graphs covering the 4 compaction parameters: detachment stress, ejection stress, E to D ratio and compressibility. We will now look at each of these in turn. Here you can see the detachment force profile for the sample. Each graph in the dashboard includes recommended acceptable values. In the case of detachment force, the green line on the graph is the upper limit of acceptability. In common with most materials, this sample shows increasing detachment force with increasing compaction and pressure. However, the key point here is that the data are well above the acceptability line, which means that the product is not properly lubricated and requires additional lubrication. Ejection stress is the stress generated during the ejection process. It's a measure of how well lubricated the tablet is. Lubricants are added to the formulation to reduce ejection stress. Products need to be below the acceptability line to be suitable for manufacturing. This sample has ejection stresses above the acceptability line, showing that further lubrication is still needed. Although the data we have is limited, other people agree that high takeoff force is a sign of lubrication problems. This results in E to D ratios of less than 1. For this material, the E to D ratio was substantially less than 1. If this were a product, we would be looking to study its lubrication in much more detail to understand the lubrication risks that might be present. E to D ratios of less than 1. Tabletability is the relationship between tablet mechanical strength and the pressure used to make the tablet. Tabletability is maximized to ensure that the porosity of a tablet is as high as possible for any given compaction pressure. This maximizes liquid penetration into the tablet and therefore tablet dissolution rate. In production, there is a risk that the operator will compensate for poor tabletability by using excessive compaction pressure to reach an acceptable tablet hardness. This will have an adverse effect on dissolution and other tablet properties and is highly undesirable. Good tabletability is therefore extremely important. Compactability is the relationship between tablet density, or solid fraction, and tablet tensile fracture stress. To avoid the risk of overcompression, it is important that adequate tablet strength is achieved using a density which does not present a risk of capping. It is generally desirable to restrict density to 90% of the maximum density of the tablet, although this is not always possible. G ratio is a normalized proprietary single tablet assessment of tabletability derived from the tabletability profile. G ratio is greater than 1 for a good formulation and largely independent of compaction pressure. Materials for which G ratio falls with increasing pressure are reaching the limits of their compressibility. Changes in tablet dimensions are frequently seen after ejection of the tablet from the die. In some cases, contraction of the tablet is seen, while in others, and in much more commonly, expansion occurs. Elastic recovery is widely held to be one of the causes of capping, a major tableting defect which requires slowing of the tablet press for resolution, sometimes with massive impact on productivity. Checking for elastic recovery during development and manufacture is therefore important. This is the Gamlen dashboard for the tablet fracture process. you can see the 4 parameters we measured displayed: tabletability, compactability, G ratio and elastic recovery. We're going to look at the data for this particular product for each parameter. In the case of the tabletability plot, it is highly desirable to have values above the green acceptability line. In this case, the tabletability of the material tested was above the line at all compaction pressures, showing that the product had good tabletability. Compactability is the relationship between tablet density or solid fraction and tablet tensile fracture strength. The green line here represents the recommended upper limit for this material of 90% density. Tablets made with a density of more than 90% are more likely to cap and show overcompression problems. In this case, the maximum density seen exceeds the 90% level. This would have to be considered along with the other tableting parameters. The tablet has good tensile strength, so in this case the high density of the tablet is probably not a problem. The G ratio is derived from the tablet tensile fracture stress and the compaction pressure. A perfect G ratio profile is independent of compaction pressure and above the green line on the plot, that is, above 1. In this case, the G ratios are well above 1, but the ratio is steadily falling across the compaction pressure range. This shows the material is reaching the limits of its compressibility and that further increases in compaction pressure could result in capping. These data would normally be looked at in conjunction with the other compressibility data when you decide how to proceed. Elastic recovery is the expansion of a tablet when the compaction pressure is removed and the tablet is ejected from the die. At the end of the compaction process, but before the tablet is ejected, a residual lateral force on the tablet remains, which is released when the tablet is ejected. In some materials, the expansion of the tablet is enough to cause lamination or capping. For most pharmaceutical materials, the axial elastic recovery, that is the change in tablet thickness, is up to 3%. The values for this material are unusually high and would probably need further investigation. The 8 critical quality attributes we measure need to be looked at together to form an overall impression of the product. They assess how likely the product is to cause problems in manufacturing. They can also be used to study the effect of composition or formulation, for example, the effect of lubricant or compression aid amount, the effect of processing and process type, such as direct compression versus dry granulation, and they can also be used to study the effect of process variables on tablet quality, such as moisture content and lubricant mixing time. The Gamlen Dashboard is quick and easy to use and does not need an extensive understanding of tableting to generate valuable results. If you would like more information about the Gamlen Dashboard, please contact us through our website www.gamlentableting.com. Thank you very much for listening.